Welcome to This Explainer. Have you ever watched a perfectly executed stunt, or maybe a rocket arcing up into orbit, and just wondered how all the chaos of the real world gets tamed by precise calculation? Well, mastering physics isn't just about memorizing some dry equations on a chalkboard. It is literally like learning to read the universe's source code. Today, we're going to unlock the predictable clockwork that governs how things move in our three-dimensional reality by scaling it down and looking at it in two dimensions. We're talking high-stakes motion, real-world engineering, and the absolute mathematical certainty that makes the impossible, well, totally possible.
Just imagine this moment frozen in time. A BMX rider completely suspended against a brilliant blue sky, perfectly halfway through a massive jump. Now, to anyone watching, it's this terrifying, heart-stopping moment of weightlessness. But when we map it out mathematically, it's just a beautifully predictable arc. See, before the tires even left that ramp, the exact landing spot, the maximum height, the speed of impact, all of it was already predetermined by the laws of physics. And before we even touch a calculator today, we really have to understand the fundamental mechanics driving that flight path. Because, let's be honest, if you get the math wrong here, gravity is very unforgiving.
Okay, let's dive into this. Here is our mental map for today's explainer. First, the physics of 2D motion. Second, the power of vectors. Third, the independence of x and y. Fourth, mastering projectiles. And finally, understanding relative velocity. Starting off with Section 1, the physics of 2D motion. Let's lay the foundation. How exactly do we describe an object moving across a surface? Up until now in your physics journey, you've probably spent a lot of time studying motion in a straight line. Like a car driving down a perfectly flat, straight road. But to describe an object moving across a surface, navigating both the x and y directions at the exact same time, we need an upgrade. And it all begins with understanding the difference between scalars and vectors. A scalar is simply a magnitude. It's an amount, like a distance. If I say I walked 50 meters, that's a scalar. It tells you how far I went, but not where I actually ended up. But a vector has both magnitude and direction. If I walk 50 meters straight north, well now, that is a displacement. It's a vector. Understanding this difference between a scalar distance and a vector displacement is the absolute bedrock of 2D kinematics. Seriously, without direction, we just can't map the physical world. Moving right along to Section 2, the power of vectors. Let's talk about resolving components. When an object moves at an angle, say an eagle diving for prey or our BMX rider launching off a ramp, we can't just plug that angled velocity straight into our standard 1D equations. It just doesn't work. We have to mechanically break the world down into pieces we can actually control. So the crucial point here is this master key to 2D kinematics, a three-step process. Step 1, you resolve that complex angled vector into manageable horizontal and vertical components using some basic trigonometry. Step 2, you treat those components as two completely separate one-dimensional problems, literally just solve them side by side. And step 3, once you have your answers, you recombine the results. Breaking down complex reality into these simple components is exactly what makes predicting the seemingly impossible entirely possible. Which brings us to Section 3, independence of x and y, the idea of two distinct dimensions. Now, pay close attention, because this is very often the biggest aha moment for physics students. If you've ever played with an Etch-a-Sketch, you know that turning the horizontal knob has absolutely zero effect on the vertical line, right? And vice versa. Well, the physical universe operates the exact same way. Let's really contrast these two realms. Imagine an object flying through the air. Horizontally, there is nothing pushing or pulling it, ignoring air resistance, of course, so its horizontal velocity remains completely constant out there. But vertically, it is locked in an invisible battle with Earth's gravity, meaning it is constantly accelerating downward. These are two completely distinct one-dimensional worlds happening at the same time. But here is the big secret. They share a single universal clock. Time is literally the only variable that crosses over between the x and y axes. The x part of the motion occurs exactly as it would if the y part didn't exist at all. Wild, right? Now for Section 4, mastering projectile motion. Let's take this out into the real world. Let's look at projectile motion, situations where an object is hurled, shot, or fired near the Earth's surface. Again, we're ignoring air resistance here just to see the pure underlying math at work. And this brilliantly illustrates the two separate worlds at play. Just look at these kinematic equations. Notice how the horizontal equations completely rely on velocity being a constant. There's no acceleration term there. But look over at the vertical equations, they are heavily influenced by g, the acceleration due to gravity, pulling downward at a constant 9.8 meters per second squared. And remember, time? That's your bridge. Time is what links the horizontal and vertical sides together.
Let's visualize this with a massive scale example. Imagine a heavy military transport plane flying horizontally at a blistering 115 meters per second, cruising at an altitude of 1050 meters. Suddenly, the crew drops a heavy care package out the back. Now, because of the independence of X and Y we just talked about, the vertical acceleration of gravity begins pulling that package down instantly. But it also retains that massive 115 meters per second horizontal speed from the plane. It doesn't just drop straight down like a rock. Instead, it traces this massive, sweeping parabolic curve all the way toward the Earth. So to find out exactly where it lands, we literally just use the vertical drop to find out how long it spends in the air, and then we multiply that time by its horizontal speed. Simple as that.
Okay, let's up the stakes a bit with a real engineering challenge. Let's bring back our BMX rider. He is hitting a ramp at 65 kilometers per hour, launching at a steep 40-degree angle. His goal? To land perfectly on top of a building that is exactly 5.8 meters tall. Now, this isn't guesswork. Life and limb are on the line here. Exactly how far away from the building does that ramp need to be placed so he doesn't crash? Now, what's really interesting about this slide is how cleanly the math untangles the total chaos of this jump. First things first, we break that initial 65 kilometers per hour angled speed into its pure horizontal and vertical components. By using the vertical equations and, of course, factoring in gravity pulling against him, we find out that his time in the air to reach that required 5.8 meter height is exactly 2.80 seconds. Then the magic happens. By taking that 2.8 seconds and plugging it right into our horizontal constant velocity equation, we find the exact distance. The ramp must be exactly 38.6 meters away. Boom. Mathematics providing perfect safety.
Let's kick it up another notch with an advanced university prep level calculation involving the legendary daredevil Evel Knievel being fired from a cannon. So he launches at 26.6 meters per second at a 50-degree angle, and he's trying to clear a massive gap of 60 meters. How do we solve this? Well, by breaking his initial velocity into its components, which gives us 15.1 meters per second horizontally and 21.9 meters per second vertically, we completely unlock the entire flight path. That horizontal speed tells us it takes just under 4 seconds to actually cross the 60-meter gap. Then we plug that specific time into the vertical equation along with gravity, and it reveals his exact height upon arrival on the other side. It's just an absolutely incredible demonstration of how these two distinct dimensions coordinate to dictate physical reality. All right, moving into our final stretch, Section 5, Understanding Relative Velocity. It is time to shift our frames of reference. To really master this next concept, you need to change your eyes, so to speak. Up until now, we've kind of assumed the ground is just standing completely still. But what happens when the very world beneath your feet is also in motion? Imagine you are walking forward on a fast-moving train. To someone sitting in a seat right next to you, you're just walking by at a casual 2 meters per second. No big deal. But to an observer standing outside on a fixed platform watching the train zoom past, your speed is your walking pace plus the roaring speed of the train itself. Measuring velocity requires a fixed reference frame. If the frame itself is moving, well, now you're dealing with relative velocity. Here is a great everyday application to think about. Imagine a girl is throwing a ball from a window down to a boy who is running across the ground at a constant 4 feet per second. To hit him perfectly with that ball, her calculations can't just be based on where he is right now. That won't work. The position, the velocity, and the acceleration of the target must all be known. The ball's velocity relative to the girl actually has to account for the boy's velocity relative to the ground. It's a dynamic puzzle. Let's move to and see how this builds into high-end aviation. Landing or launching a multi-million-dollar fighter jet on an aircraft carrier is literally one of the most difficult tasks in engineering. Why? Because the carrier is cruising through the water at 50 kilometers per hour. If Jet A takes off at a horizontal airspeed of 200 kilometers per hour, as measured by a completely stationary buoy out in the water, calculating its speed relative to that moving runway is a matter of life and death. The velocity of the jet relative to the air relative to the ship, and the ship relative to the water, every single piece of that has to be factored in perfectly. But honestly, mathematically, we solve this with a beautifully simple visual tool, the vector triangle. Relative velocity problems are really just another form of vector addition at their core. If we know the absolute velocity of object A and the absolute velocity of object B, we just draw a triangle. The line connecting the tips of those vectors gives us the relative velocity of B with respect to A. By taking the time derivative of the relative position equation, we can just solve for any unknown side of this triangle. It is incredibly elegant. So what does this all mean? What should you really take away from this explainer?
Mastering these 2D vectors, breaking down complex angles into their horizontal and vertical components, and shifting your frame of reference, it means mastering the predictable clockwork of the physical world. These equations aren't just arbitrary numbers on a page. They are the actual inviolable rules that govern everything from a drop-in care package to supersonic flight. The universe literally has a code, and now you know how to read it. But consider this before you go. If we can use math to predict the exact trajectory of a fighter jet landing on a moving runway in the middle of the ocean, what other chaotic forces in your life are just waiting to be mathematically decoded?